Okay, so we go ahead and look at the top one. So I will say on this one, I think they're being a bit wankerish. Dang, I shouldn't have recorded that. So major product of this reaction. So when we first look at this, first thing that jumps out at me is we've got carbonyls. So I'm looking at nucleophilic addition. Typically, I see Br2. I know Br2 is an electrophile. And I know as an electrophile, it very commonly does that alpha halogenation reaction. So we do pull off that acidic hydrogen and we replace it with bromine. Okay. Why does this one scream at me? Well, we have a methyl ketone or a methyl carbonyl. Right? In that scenario, what we should be going through and doing is the haloform reaction where we produce CHI, which is, well, ignore I said anything because it's not there. So this is effectively trying to trap people in a memorization process. That haloform reaction, for anybody that memorized it, hopefully also memorized the secondary conditions. What are the secondary conditions necessary for the haloform? It needs to be a basic environment. Okay? We can't run it under acidic conditions. Okay? So as soon as I looked at this, I was like, oh, dang, are they tripping and just saying we're doing something different? They are not running the haloform reaction. The haloform reaction has to run under basic conditions. So if we process through what happens, acid's the most acidic or most reactive thing here. It's also the most acidic, but most reactive is more appropriate. Okay, we've got our phenyl, we've got our carbonyl. We have that alpha hydrogen that is acidic. Okay, it is not acidic as H3O+. So what happens? The lone pair electrons on our oxygen react with our H3O+. I'm just going to draw it as H+. Set it up now with an activated carbonyl, making that hydrogen that much more acidic. So we can go through and form, oops, that's not resonance. Our enol reaction. There's our OH, there's our double bond. Remember, we still have the resonance option within that. Electrons come down, and we're effectively putting negative charge out on that carbon. Okay? We would never show the negative charge in a mechanism because, say it again? It's not a good or not the best resonance structure. And I should have phrased that a little bit better. We should never show that negative charge in this mechanism. What conditions are we under? Oh, acidic. H+, positive charges. We should never see this negative charge. It's useful for us to see and acknowledge its existence so we can predict chemistry. But if we're asked which of these things exist, this does not exist in this reaction because we're under H+. Okay, but this flags our carbon as being our nucleophile. That can react with our bromine, again, per typical, fairly sloppily, bless you. We get our pH, our carbonyl, our CH2 with a bromine on it. Okay? Do we still have those alpha hydrogens? Yeah. Yes. So could theoretically this reaction run again?
Yes.
Theoretically. Why does it not? When we run this reaction, what was the critical first step? The H3O+, protonating that oxygen. That's what drives this mechanism. As soon as that's protonated, the rest of this now kind of follows suit. If we now go ahead and look at that oxygen in our product, is it as basic as it started?
No.
No, why not? An inductive effect. The bromine is electron withdrawing. It's drawing electron density into the structure, which means that oxygen is less basic. Since it is less basic, it does not do our initial step under acidic conditions. Since it doesn't protonate, we never activate the carbonyl, so we never get to a position where we can actually have an acidic hydrogen. Our reaction stalls. Under basic conditions, the first step is the deprotonation, right, of our enol. In this case, the hydrogen is more acidic. So under basic conditions, it continues to react because we've created a more active substrate. Under acidic conditions, we haven't created a more active substrate. The reaction stalls and it finishes after one step. So if we go back and now look at our answer choices, there should be two answer choices that are kind of screaming at us. This one, oh, it did show up. That CHBr3, that's our standard haloform leaving group. Okay? This is a legit trap question. Do you acknowledge that when you run that haloform reaction, it must be under basic conditions? Or did all that you memorized was carbonyl, alpha hydrogens, bromine? Okay? So it's all coming back to what level of detail you've memorized, or do you understand the mechanics behind each of those reactions? Kind of makes sense? What does that mean? That answer is wrong. It's there as effectively the trap. You just memorized or tried to memorize your way out, and you didn't memorize enough information to actually make it useful. Okay? What happens instead? You do a single substitution. You get C. Okay? Other things that we could throw on here. D is a step on the way to B. So if you'd memorize some parts of the mechanism to get to B, maybe you'd see D and be like, why are they showing two answers on that same path? That seems a little bit questionable, okay? And that might be enough of a pause to make you snap out of and remember your mechanistic detail. Otherwise, yeah, you gotta be real careful with what you memorized. Okay? Where's A coming from? A is coming from EAS, okay? We've got a deactivated ring. We'll talk about that when we do some EAS reactions. But we've got a deactivated ring. It's not going to react very easily without some big catalysts. We aren't catalyzing this with enough to actually get this running. Okay, sir.
Is there any other functional groups that we'd have to care about that could potentially do the, what's the term for it?
Haloform?
Yeah, haloform.
Yes. So when we're looking at our yes and no, there's one other reaction. It's not running the haloform. What we've done here is alpha halogenation. It just looks like haloform, and that's where we have to be careful. With alpha halogenation, your ketones, as long as you have an alpha hydrogen, you're good to run. Okay. If we go through and changed our starting material, we're going to look at A. Whoops, let's not do that one. That side. And we made this an OH. We now have a carboxylic acid. The carboxylic acid is not susceptible to alpha halogenation. We still have the alpha hydrogen. Why is it not susceptible?
It's not susceptible because the hydrogen is not acidic enough.
A little bit more than that.
Because the OH is the most...
There it is. The more acidic hydrogen is on the OH, or carboxylic acid. And if we deprotonate that, what happens? That negative does resonance inwards, effectively nullifying the ability to remove the alpha hydrogens. It changes the chemistry dynamics so much that we lose that alpha hydrogen chemistry. Okay? There are ways to get around that. So we could theoretically start with a structure that looked like this and end with an alpha halogenation. How do we pull it off? It's not really a catalyst.
By changing it into a more reactive, something that's up the ladder.
The carboxylic acid is problematic. We don't want the carboxylic acid there. So what we have to do is nullify its presence. Okay? We can do that by converting it into an acyl halide. The acyl halide can't do resonance inwards, which means it doesn't get that competing resonance. Whoops. Doesn't give us that competing resonance, which means these hydrogens are acidic, and I can indeed go through that process. But if I want the carboxylic acid back, all I have to do is now add water. Water does a nucleophile attack, replaces the bromine. So you're running through a multi-step process. You have to convert the OH to bromine, okay, or chlorine. So you're using PBr or you're using thionyl chloride. Okay. You then run your alpha halogenation. Okay. That can be your Br2 and mild basic conditions. We have to be careful with the base that it's non-nucleophilic because we've got an acyl chloride. Okay. Then you can go through and undo your very first step and revert it back to the carboxylic acid. That's a sequence of a lot of steps, and it looks relatively simple. Okay? And in that simple approach, we wouldn't think it works because someone was able to discover it. It gets named for them, and that's where we get the nasty long name, Hell-Volhard-Zelinsky reaction. That's this reaction. So it is taking advantage of that alpha halogenation. It's pointing out that we don't have activity with the carboxylic acid, but we do have activity with the acid derivative. Okay, so there are other functional groups that can come into play. That's going to be one of the bigger ones. Other questions on it?
I just want like a quick clarification on something. For the last step of the equation, are you kicking out? You're kicking out that hydrogen, but like from the green to the red figure right there, you have the hydrogen, but you aren't showing it getting kicked out, but it's not in the final one. What exactly happens there?
That's a CH2. There's not a hydrogen being kicked out in the green to the red.
No. At the oxygen is what I'm saying.
Oh, my bad. Sorry. I didn't see it.
Yeah.
You're right. That hydrogen should be 2 steps. That hydrogen comes on and off the structure effectively at will. This is something that is one of the more challenging things with second semester.
Okay.
We effectively protonate and deprotonate at will to decide how we want our reaction to run.
Okay, yeah.
I would argue more than likely what's going to happen is you're going to have it protonated under the bromine, with the bromine on, and then you follow it up with a workup to neutralize the acid. There goes the hydrogen.
Cool. Yeah.
Right? So we're not being explicit in the reagent that we're showing to remove that hydrogen.
Yeah.
Good question, and thanks for following up on that, Aiden. What?
I had a question.
No.
No, it was Louis' good question, and then you following up pointing out what I didn't see, which you were probably in the process of fixing me on. But
yeah, I just.
Next one. What changes in the next one?
Basic conditions.
Now it's under basic conditions. With the basic conditions, this reaction is going to run. Okay, how much is it going to run? Until it can't run anymore. Okay. What's that?
The ring's also not aromatic.
The ring is also not aromatic.
I mean, that matters, but what?
And you're saying that because we started with an aromatic ring up here? Is that why? So I'm hemming and hawing on that a little bit. Where's the chemistry that we talked about in the first reaction?
Well, it's not in the aromatic ring, but all the chemistry on this one is on the ring. I don't know.
So, and that's the phrasing actually I want to call attention to. Where's the chemistry with our very first question?
But it's going to be.
It's dealing with that alpha hydrogen. That's the chemistry. When we go and look at the next one, it is very common for people to go, oh, it's a ring. It's not a ring. That is 100% irrelevant. We don't care that it's a 5-membered or a 6-membered or a 4-membered ring. What we care about is what's the chemistry. If it's a benzene, that's a whole different system. Because if it's a benzene, what do we say? Blanket first pass, it's aromatic, it shouldn't react. Okay? Yes, there's nuances to that, and we can pick that up again when we move to EAS. So when you look at this, I don't want you seeing a ring. What do I want you seeing?
The alpha hydrogens.
I want you seeing 3 alpha hydrogens. What did the rest of that structure do?
Nothing.
absolutely nothing. So it is irrelevant to your discussion, your phrasing, your terminology to even breathe life into it. It's irrelevant to the overall molecule. Keep your focus where that chemistry is. That's our alpha hydrogens. Right? We're going to run a similar mechanism. Do you actually want the mechanism?
Yeah.
3. Okay. Our base comes in, deprotonates. We got the negative charge. That negative charge is okay to show. Right? It is officially on the useful structure, not the best structure. The best structure would be the resonance I'm not showing. Our excess bromine in place, our electrons can come in, attack. And then this is the important structure. Where we've got the bromine on there. Because Louis asked a good question in the previous one. We had a hydrogen that we had to remove. Do we have to worry about that hydrogen now? From the oxygen. We had a hydrogen that we had to, why do we not have to worry about it now?
Well, because there's no reagent that's adding the hydrogen to it, or am I saying that?
Yeah, not quite the answer I wanted, but that's the right idea.
Okay.
In the previous case, we had to put the hydrogen on. Why did we have to put that hydrogen on?
Acidic conditions.
We were under acidic conditions. We're no longer under acidic conditions. There's no reason to have the hydrogen on there. Does that make sense? We weren't wrong. It was the slight phrasing. Right? So cool. This sets us up with our product after one run. That reaction ran because of what? Basic conditions. We needed to neutralize the base by removing an alpha hydrogen. So that alpha hydrogen had to be acidic. Was it acidic? Yes, that's the resonance. We look at the product. Do we still have those alpha hydrogens? Yes. Are they more or less acidic than where we started? They are more acidic. Okay? How do we know they're more acidic? Of course, I didn't draw any space.
Well, I know because I forget what phrase you used, but it's because the BR was added. But what did
Well, wait. Didn't the BR being added the last time cause it to not react?
Yeah, but the environment's different.
Okay, so how is it different? Just saying that I have bromine on there changes it isn't quite good enough.
Okay.
What we're comparing is this structure to
Oh.
our red structure, the
Oh.
conjugate base. How are they different? Do they have the same charge?
Ish.
Size?
Yeah, no. Well, not really. Well,
So,
basically.
and this becomes one of the questions, is when we talk about these charge, size, electronegativity, where is your focus? The atom that is reactive.
Okay.
The atom in the red structure is carbon. The atom in the purple structure is carbon. So when we say charge, it's the charge on that atom. It's identical. When we say size, we say the charge on that atom. It's carbon versus carbon. It is identical. The rest of the molecule is not relevant yet. Okay? You must start centrally first and slowly back out to the larger molecule because we're looking for primary differences at that small level. Okay? So size, electronegativity, all the same. So we move to resonance. They both have resonance. There's no extra or fewer resonance for either one of them, which then moves us back to the exact same explanation we used for the previous one, which was induction. Right? In the previous case, we said the bromine was withdrawing electrons. But by withdrawing the electrons, it made our oxygen less basic, and we did that to act as a base. By withdrawing the electrons, what does the bromine do to our negative charge? It draws it into the molecule, making this negatively charged species more
Acidic.
stable than our red structure, which means the black structure is indeed more acidic. Which means
It can react again.
the reaction keeps ripping. You put on another bromine, it now becomes even more acidic due to even more inductive effects. Right? Do we have still more hydrogens?
Yes, but they're not acidic
Why are they not acidic?
because they're not part of they're not next to the whole double bond. I don't know how to say it.
The alpha hydrogen being next to, whatever that word is, next to our carbonyl allows for that resonance stabilization. We are not getting any stabilization for any of those other hydrogens, which means they aren't acidic. Okay, you'd be forming a negative carbon that's not resonance stabilized. That's not more stable than our negative oxygen that came in and acted as our base, which means we run the reaction 3 times, we brominate in all 3 of those positions, and we get the final answer of A.
Just a quick question. In the previous problem, they just had BR2, but this is BR2 excess. What's the difference? Does it just mean that there's
Red herring.
it's just nothing?
So BR2 excess, that word excess can be used as a hint that you should keep going. It could also be used as a distractor that they're just trying to mess with your head.
Okay.
They don't have to show it. They don't have to not show it.
Yeah. Okay.
So I've seen it where it's useful. This would be a case where you could argue it's useful. I want to keep going. Okay. I've seen cases where they show it and it's not useful.
Okay.
So I would back away from the use of excess as any kind of extra use information. Focus on the chemistry of the reaction.
Okay.
Okay. The one exception, if you're trying to just memorize your way out, use whatever tool you've got. Hope for the best. Hope it's being used in a nice way. I tend to not believe things are nice.
Yeah.
Other questions on it? Next one, what do we see? Do better than reagents.
We see it looks like it's going to be, it says substitution, but what?
I'm going to revoke my sassy comment. I didn't actually see the question. It was too far zoomed in or zoomed out.
That's crazy.
I apologize. Reagents, what you're being asked for is what reagent you're going to use in this chemical reaction, so I can kind of accept that. I do apologize.
Our track record with reagents It's not like we were gonna know this one.
That's a little pessimistic. When we go through and look at this, what's happening?
Yeah.
Okay, so we can go through and look at these pieces. Okay, we're putting on an ethyl. Putting on I like better than the word addition. What's the problem with the word addition?
Oh, because it says substitution.
It's officially a substitution. Okay, we aren't actually, there's a gray area for calling it an addition, but it's officially a substitution.
Yeah.
Right? What charge is the carbon that came in? Do we know anything about that carbon? Okay, so we've got a red carbon and a blue carbon. We've got that new connection between them. Okay, do we know anything about either one of them? Okay, blue carbon, if we look at our starting material, just has carbons and hydrogens. Come back to that. Okay, we're looking at nonpolar covalent bonds. There isn't a giant red flag unless you happen to remember the word that Aiden just mentioned or the previous two questions we just talked about. Okay, what about the other one? How good are you at nomenclature? You're gonna be like, well, I suck at nomenclature. That's kind of okay, but this level of nomenclature you shouldn't be sucking at. What is iodo? Okay. Bonded to what? Two carbons. CH2, CH3. That nomenclature, or that level of nomenclature, should be well within your capabilities of being able to process. When we go through and look at that, there's our blue carbon. I guess I can make the other one black. Okay. Why is the blue carbon the relevant one and not the black one?
Oh, that's the one that's going to get the charge.
Why is that the one that's going to become charged? The iodine is more electronegative than it. We're looking at a polar covalent bond. If we look at that bond, what would we expect to have happen to the electrons in that bond? Where would they go?
With the iodine,
With the iodine, because
it's able to hold that. And
it's more electronegative, which means what happens to the blue carbon?
it has a positive charge.
It becomes positive, which means what charge? Whoops. I should have drawn it in red. I apologize.
That's ugly.
Man, this question is just full of mistakes. Which means what charge must our blue carbon be?
Negative.
The blue carbon must somehow come out negative. It looks neutral right now. What could we potentially do to that neutral carbon?
Deprotonate.
We could remove a hydrogen. That hydrogen is removable because
Carbon is acidic. Or acidic.
why is it an acidic hydrogen?
Because it is connected to a carbon that is a part of the
Carbonyl.
carbonyl.
Okay, we're at that alpha position. We have alpha hydrogens. So that does make sense. So we could deprotonate that. Do we have other alpha hydrogens to worry about? Yeah, in fact, there's alpha hydrogens on both sides of that carbonyl. That's what the question is actually asking about. How do we differentiate which hydrogen we remove? How do we decide? You okay? You just throwing stuff? Everybody's favorite stuff from 152.
Stereochemistry.
Kinetics and thermodynamics. This is looking at the kinetic reaction or the thermodynamic reaction. We're concerned about forming the enolate on the least substituted versus the most substituted. Okay, so we have to be careful with the base we choose. We have to choose a base that favors the kinetic route over the thermodynamic route. How do we decide how that runs? If we don't remember, that's okay. What I would recommend you do is start memorizing our differentiation for our kinetic versus thermodynamic reagents, most and less substituted reaction running. If we're looking at a kinetic base, we're looking at LDA. Thermodynamic, we're looking at our O minus, for lack of a better word. LDA or sodium hydride are our big ones. What is the reactivity in LDA? Let's try it this way. What's the reactivity in NaH? The negative hydrogen. What's the reactivity in LDA? Negative nitrogen. What's the reactivity in the thermodynamic one? I already did it. Negative oxygen. This is where we get hydroxide, T-butoxide, and all of those fun things. They're all that negative oxygen. Those are thermodynamic. Okay. What does that mean for us? What we're looking for to get the kinetic product, because we want the most accessible one, we need an LDA or a negative nitrogen or a negative hydrogen. This goes again back to nomenclature and trying to process through to figure out which one of those is then going to be our best bet. And what do we see?
LDA.
Okay. There's one that's literally LDA. Okay. Lithium diisopropyl amide. I believe as a name, interestingly enough, they put at the very front of the exam saying that this is what this means. It draws the structure out for you. Okay. These ones, A and C, are also amides. How do we differentiate?
Like, how do you mean? Like,
These are negative nitrogens.
yeah, but
So why lithium diisopropylamide, LDA, and not sodium amide or lithium amide?
Those are more selective.
Yeah, it is more selective. Can you elaborate? Touche.
It's because it's got like more stereochemistry, so it's like harder for it to reach the one by the methyl group. The hydrogen, the
Sort of right word, not stereochemistry, but sterics, electron bulk. Why does that matter? What are we trying to do? What does our species need to do?
It needs to deprotonate.
It needs to deprotonate. What happens if we pick something like sodium amide or lithium amide?
They
How
can-
big are they?
Very small, they can easily deprotonate the other side.
Well,
they're
so
very-
that's that. They're very small, which
Yeah.
means they can.
Deprotonate.
Act as a nucleophile?
They could act as a nucleophile.
Oh.
I don't want it acting as a nucleophile. I want it acting as a base. What they're throwing in here is a secondary. Do you know the difference between our bases versus nucleophiles? Okay? So not only do we get this issue of kinetic versus thermodynamic, but we also get an issue of, do we understand the difference between a base versus a nucleophile? Yay! Multi-layered questions. Okay? If you'd memorized LDA, you were probably fine. You didn't. Oh well.
When you brought up the up there, and I saw it, so.
Questions on what that one had? As I'm going through and doing this, I do want to point out for sure within the new version of the ACS, they do have typos for the record. I've caught a couple of them, and if you use the book in the tutoring center, they might actually have it flagged within that. What is the major product of this reaction? So what do we see? I see a sodium next to that, which means that sodium comes out as a positive. I can ignore it. That gets me a negative oxygen. I get negative OCH3. That negative then could act as a base or nucleophile. If it acted as a nucleophile and attacked the ketone, we'd get a hemiacetal. Our hemiacetals aren't stable. It's going to revert back to the carbonyl. Okay, we could also scan through to see if we had anything like that. Sort of do with A, but we don't see the CH3. So A doesn't make sense there. If it attacked the carbonyl, we'd form the tetrahedral intermediate, reform the carbonyl, and kick out OCH3, which happens to be the exact same thing. Which means the nucleophile characteristics are effectively a moot point, and instead it needs to act as a base. As a base, it's going to remove the most acidic alpha hydrogen. There are two alpha hydrogens to choose from, terminal or internal. Which one's more acidic? Internal because?
It's connected to
two resonance directions to stabilize. Okay? Which means that first step effectively puts a negative charge on that carbon. What do I need to stabilize that negative carbon?
positive.
A positive. So this is where I could look at that next step, and what do I see within that? I see a CH3 bonded to a bromine. If I want to draw that out better, I might actually draw it as H3C. I have a polar covalent bond there between the carbon and the bromine. What do I want to do with those electrons? Shuttle them towards the bromine, which means the carbon becomes positive. What did I just find?
Your answer.
Negative and the positive, and it's now just a question of hooking those two up and setting up my answer, which in this case looks like C. A, I quite frankly can't figure out what they did, at least quickly. B, they deprotonated the other side, okay, the less acidic hydrogen. C, they deprotonated the correct one. And D, they added an extra carbon out there. Again, I'm not quite sure how they pulled that one off. Yes, sir?
So OCH3 just deprotonates one of the hydrogens?
Just deprotonates. All it does. Deprotonates and sends this up with a carbon nucleophile. That carbon nucleophile can then go through our substitution reaction. This is one of the most common methods when you have those two carbonyls next to each other, that alpha hydrogen in the middle. It's almost always to deprotonate, activate it as a nucleophile so that you can add more carbon. Real fancy names got dropped for that in the last unit. I think you get the malonic ester synthesis or acid synthesis, or the acetoacetic. I think this is actually acetoacetic ester synthesis. Okay. They're naming the starting material that you're working with, and it has to do again with the acidity on that. Why would these be potentially powerful reactions? What did they generate? Yep, a negative carbon. Why is that cool to have a negative carbon?
Because it's more like, it wants to be neutral even more.
It is more reactive, but why do I need negative carbons? I can build larger carbon structures. Carbon is our fundamental building block on which we lay everything. If we can't put more carbons next to each other, everything we get is small. So this allows us to build carbons upwards, okay? And at a relatively controlled rate, if you factor in decarboxylation and all of that, you can add 2, 3 carbons. You can do 2 or more carbons depending on the starting ester that you pick, okay? So that's a pretty powerful tool, and on top of which, if we consider how we got it, we get it by adding a base. Not a particularly like wicked, oh my God, this is gonna melt my face off base, but just a standard kind of run-of-the-mill base, okay? How do we get a Grignard reaction to work? I need to mix it with magnesium. I need to mix it in an inert atmosphere. It has to be a closed system. I have to ensure there's no water. There's all of these secondary considerations that stack that make that reaction much more difficult to run. Okay? Here, I just throw a base at it and I get a nucleophile. Like, that's pretty legit. Okay. Last one is 2 cut off. Let's just run it anyway, based on what we see.
Well, but we don't even see
What do
the
you mean?
carbon chain.
Oh, don't owe me. It's not that bad.
Yeah,
With like tears streaming down.
If you look at the product, we see 2 carbonyls. When we look at the reactor, we had 2 carbonyls. More than likely, what's between those 2 carbonyls?
I don't know.
nothing.
Bullshit.
Some carbons.
Oh yeah, well yeah, carbon, but like
Yeah.
you seen the product is what am I trying to
What if
say?
there was like something else there instead of the O though?
Oh, I mean, there perfectly well could be. So the point of this is trying to predict based off of what you see. Okay? The vast majority of the time, what are you looking at when you look at the exam?
Before and after.
Wrong information.
Oh.
Almost always. Right? The vast majority of the exam is built with incorrect stuff. So if you can start piecing together things of where these patterns fit, that's a powerful tool. Okay? Carbonyls, I would bet the rest of that structure is going to be there because that particular site is, that one's reactive because that's sitting between 2 carbonyls. That seems pretty legit, which means I want to now somehow add an extra thing. I want to add whatever this is, whatever that line is. That could be a CH3, that could be a benzene ring, I don't know. There's something there, but if I call it a CH3, how could I go through and do that? What do I need to do?
Depropionate.
I need a base. Right? Red was my theoretical starting material. There's even a little dingus right there. See the little dingus? Matches that dingus.
Yeah.
Right?
That's a fun.
I don't have a CH3, so what else do I need?
Which we could just we just used what we just did. Yeah,
And now,
it's like exactly what we did.
oh yeah, where's the book? What page was this?
199, question 9.
Did I just BS my way into it? Oh, look at that. That's
Yeah,
pretty.
You
That's
actually got it.
pretty dang close. Okay. The fishy little dingus hanging down was not a methyl. It was an ethyl, a CH2, CH3. So that's CH3, CH2, Br. And then I need to add a base.
Well, we
And
could,
if
use, we could use just what we did in the previous one. There was CH2, CH3 connected to an I.
The
Or-
previous one was just CH3. It was a methyl.
No. I mean before.
Yes.
Yes.
So then it's going through the answers and saying which of the answer choices give me a base and that halogen thing. Only one of them hits it. Only one answer choice. So just being able to approximate where some of that chemistry, the book doesn't belong over there, right, allows me to navigate a lot of those pieces. So look for the things that stand out to you, and hopefully you've seen enough that some of these patterns start to move through. Kind of, sort of?
Kind of, sort of.
That, come on, I didn't even have it, and that was pretty
really
good. I didn't need that though, but I appreciate it.
Go. Slay?
Yeah.
Okay.
That was the
What's that mean?
first time anybody has ever heard anything I've done is slay. Okay, and you said EAS.
Who said?
Malia, you said EAS, right?
What?
You said you wanted EAS? Didn't you?
Yes.
Actually, now that I do that, since you said it, you can hold the book open. EAS. You wanted EAS questions.
Now I gotta find it.
I don't think it's recording
This
that.
one
It'd be
looks
kinda
kind of
funny.
That one kind of looks
Which one?
fun.
That beige?
Yeah.
What's wrong? Fun. Fun's a good thing.
Those are good homework questions, right?
Yeah. Oh, can I chop off
You
top of that?
good? Here, you
It's
can
good
redo.
enough.
Here, I got you mine. Here,
It's good enough.
here, or I'll hold it like this. So that way you can.
It's not for me, it's for everybody else. I cut off the CL.
Well, my hands are, I feel so bad. They're crusty. They got eczema.
Don't worry. See, your hand's all gone.
Look,
Okay, so if we look at the first question.
so bad right now.
What is the major product? Oh, you picked like. Wow.
I hope these looks fun.
Is it CL at the very top? Like, I can't really see.
So
It looks like.
this is not EAS. This very first question is not EAS. Are any of the other ones EAS? So the second one is, at least. 12 is, 13 is, 14 is. Okay. So what is the first one? So for EAS, electrophilic aromatic substitution, which means we are reacting a positive with the benzene ring. Okay, if we take a look at our very first reaction, what do we see? I see a benzene ring, that's lovely, and then what am I reacting it with? A negative oxygen. That's why it's not EAS. Okay, it doesn't fit the pattern at all. That's because it's not EAS. It's what's called as NAS.
It's just the
Whoa,
opposite.
what's that?
Nucleophile aromatic substitution.
Whoa.
Right?
That's way
So that chemistry doesn't show up quite as often, but it does show up and it does require some special kind of considerations. For those people in lab, when we talked about EAS, and actually people not in lab, when we look at an aromatic ring, how would we expect it to react?
There's a nucleophile.
As a nucleophile. It's a source of electrons. We would absolutely expect the aromatic ring to act as a nucleophile. This is what EAS is talked about first and foremost. It turns out that somebody either accidentally stumbled across or said, well, it's only got a bunch of electrons in it because of all those rings. What if or all those double bonds, what if I add things to it like a nitro? Because if I do a nitro, what charge did I put right next to the ring? A positive. And what is that positive charge going to do? That ring looks so bad.
It's all good.
Electrons through resonance?
Chemistry class, not our class.
It's going to suck those electrons out of the ring. If it sucks those electrons out of the ring, can the ring act as a nucleophile anymore? No. Okay? So if we tweak our starting material enough, what we can do is suck so much electron density out of the ring that it does not act as a nucleophile. Okay? And if we go through and look at our starting material here, you'll see that they've written NO2. Okay? I genuinely think that's a little bit misleading, which is why I believe on the last exam I actually drew up what NO2 was on the board. What you're looking at is a positive charge immediately next to the ring. Okay? That is electron withdrawing. We dropped 2 NO2s on this ring, which means really electron withdrawing. Okay? So this ring is exceptionally deactivated. Electrons are being pulled out immensely. Okay? When we're talking about doing the NAS reaction, we are running a substitution. The hydrogens would not be a predicted thing to do our substitution for, because if the hydrogens came off, they would be positively charged. That doesn't make sense in a nucleophile-rich environment. So what we're talking about is something else being substituted. Well, what else is on that ring that could potentially be substituted and hold a negative charge? All those chlorines. Okay? Conveniently, they gave us, or rather inconvenient, they gave us 2 chlorines to choose from. Why?
Make it hard.
They want to see, do you understand which chlorine should be substituted? How do we know which chlorine is substituted? Everybody's favorite 9-letter word. Resonance. So we would have to look at resonance through this. If we're going to run this reaction, the negative oxygen will come in and directly attack one of those sites. I'm just going to pick that one, and we'll talk about why I picked that one in a second. Positive, positive. When we attack that one, what happens? Officially, it's all the way up at the top in the darkness. Get used to working in the darkness. You can deal with it. Sun's going to blow up in 1,000 years.
1,000 years?
I
I'll
don't
be
know.
dead.
Yeah.
So.
We would exceed the octet. So it's not just the nucleophile comes in and attacks that carbon. What else must happen?
You gotta move the.
You got to move that pi bond. So that pi bond that I drew in there to make it, to make that exceeded octet a little more relevant, what we want to do is shuttle those electrons. We will shuttle the electrons to the carbon away from our exceeded octet, putting the negative charge right there. Okay? What if I had attacked the other chlorine?
Same thing.
Negative charge there, chlorine, OCH3. Okay. Same thing's a little bit of a overstatement. Same general concept, okay, fine. Which of these two is a better outcome, blue or black?
Black.
Why?
The negative is it wants to go to primary, not tertiary. I don't know. What's the word I'm looking for? You know.
So we can reference substitution patterns, primary versus secondary versus tertiary. Negative wants to be on a primary. What rule are you using to deal with that?
I don't know. Or I always say.
That's our substitution pattern in our, oh crap, I really hope I don't have to evaluate that. What should we look at first? Charge. Are they both charged? Yeah, okay. What's the next thing? Size. What atom is holding that charge? Carbon. Is there a difference?
No.
No? What's the next thing?
Resonance.
It's got resonance.
Electronegativity.
Oh.
No difference. Then resonance. Okay? So you said resonance. What are you saying?
There's resonance.
Where's their resonance?
It's then positive.
Everywhere.
I can move that negative in towards that nitrogen. That's a resonance that would stabilize, theoretically, the positive nitrogen. Okay? Theoretically, because if you draw that out, that still stays positive. But our electrons shuttle out. Do I get that resonance option with the black one?
No.
If I shuttle those electrons in, I could put them here. If I shuttled those all the way up to here, I could get the electrons there. I would get all of my negative electrons in places that I cannot resonance stabilize out to the nitrogen, which means the purple one results in more resonance options. Because the purple one results in more resonance options, what does that mean? It's the more likely place for that OCH3 to attack.
Isn't that making it? Never mind.
So there's
Okay. Once we're satisfied that it's okay to attack, now what could go through and happen? We could reform the pi bond, but now we would kick out the chlorine. So we would get the OCH3 replacing where in my drawing, it's the red chlorine versus the black chlorine, my goofy chlorine. So I would get the answer choice of C. What we're taking advantage of is resonance. Is this something you can absolutely memorize? Yes. I can tell you right now, I was very scared looking at this question because I did not memorize it and I did not know what the answer was going to be. I am mildly shocked and mildly happy that resonance allowed us to see that answer. You don't have to know the answer if you know how to move electrons. Kind of, sort of?
kind of, sort of.
Question?
No.
Okay.
I'm just looking.
So officially NAS, there's another one. All I know is the name of the intermediate, the benzyne intermediate. Okay. So there's two reactions at the end of the EAS or the aromatic unit. One is NAS and one is the benzyne intermediate. I want to say it has another name. The benzyne intermediate's a really goofy one because in the benzyne intermediate, what you form is this glorious molecule. For those ignoring that, that's like an ooh-ah moment. That's a benzene ring with a triple bond within it. Okay, thank you.
That's so crazy. That is absolutely so
Okay.
scary.
Everyone take a picture.
That's a goofy molecule. We get all sorts of weird chemistry happening with that. You can go through and actually make that one, believe it or not. And that one sets up other weird kind of substitution reactions that you're getting multiple products that can potentially come out of it. Okay, so you probably will see a question on the benzyne. Like I can almost guarantee it because everybody thinks that's a really cool looking thing. See, including you guys. You guys all went ooh and ah. See, it's your own fault. Okay, and then you'll probably see one or two questions on the NAS. The rest of that would be our EAS stuff. I would bet that unit is probably 10 questions, but I'm really just guessing. Okay, so you're looking at probably 5 to 7 questions on EAS chemistry, which includes aromaticity as a topic. Kind of, sort of?
Kind of, sort of.
Okay, so it's actually a move to where you said you had questions as opposed to dealing with the NAS nonsense. And we can instead look at EAS. Okay, when we move to EAS, which the benzene derivatives would be the most reactive and an electrophilic aromatic substitution reaction. Okay, what I would use in this case is, again, recognizing the basic fundamentals of what an EAS reaction is. What does the aromatic ring act as? Don't break it. What does the benzene ring act as? A nucleophile, aka, that may have been a bad lead-in. Thank you, that wasn't horrible. Okay. A source of electrons, which means we need to go through and look at our answer choices and say which of those would supply us the most electrons. The one that supplies us the most electrons is going to be the most reactive. Again, with that misleading NO2, if we remembered what that NO2 looked like, what charge is the nitrogen? Positive, which means what is it doing? It's withdrawing electrons from the ring. Okay? That's making it less of an electron source. That should be an immediate red flag that that's bad. Okay? SO3, we've seen that structure show up in multiple cases, but there's our SO3H. Okay? Again, red flags being in those pi bonds. What can those pi bonds do? Resonate where the electrons go where?
The,
To the oxygen, because
that's actually.
oxygen is more electronegative, thereby doing what to our our sulfur? Making it positive. If we've made it positive, what does that do to the ring?
Draws up electrons.
Draws up electrons, also not good, which then leaves us with two potential options, A or D. What's the difference between A and D? Oxygen. Okay? How is that different? Where's the difference between our carbon and oxygen?
Electronegativity.
We could reference electronegativity.
You reference size. You're the one that says they're the same in the row, so I feel like it's unfair if you reference size.
Okay, so we can't reference size. Again, what are we trying to reference?
Resonance.
What's the reactivity we're looking at? What electrons?
What do you mean?
Which nucleophilic electrons? What are the electrons that we're being asked to evaluate?
The ones in the ring.
The ones in the ring. What I care about is those electrons. So when we go through and say charge, we're talking neutral because the pi bond on the ring is neutral. When I say size, it's same. When I say electronegativity, it's same. The difference I'm looking at isn't an atom effect, it's a molecule effect. How is the substituent affecting the ring? What's my very first molecule effect? Charge, size, electronegativity,
Resonance.
resonance. Does the carbon or the oxygen have the ability to resonate electrons into the ring? As it does, what charge does it build on my carbons? Negative, thereby making it a better source of electrons, thereby making it the correct answer. Okay? Can this also be memorized? Yes. Okay? This is looking at the atom effects, okay, of the substituents on the ring. Okay? It can be uber memorized according to the textbook and listing all the possible substituents that could go on a ring. I think that's a horrible idea. Instead, what you should be doing is what the lecture videos tell you to do. Look at atom X connected to the ring. Does atom X have more electrons or less electrons than hydrogen? More electrons, activated. Less electrons, deactivated. If you've got that context nailed down, you can now apply that logic through without having to memorize very specific reagents for it. Kind of, sort of? Which substrate is the most reactive with respect to nitration by electrophilic aromatic substitution? What are they having you do?
It's the, well, we're trying to put nitrogen on the thing, so it's asking like which, what do you mean? What's your question?
What are they asking you to do?
Put nitrogen on.
You're doing the exact same thing that you just did. There is no difference between this question and the previous question. All they've done is added more specifics. Those specifics aren't changing any of the details of the overall reaction. You just have to understand how you build those pieces outwards. Okay? Again, the nitro, you're looking at the nitrogen with the positive charge immediately next to the ring. Positive charge would deactivate the ring, so is that most reactive?
No.
No. Chlorine. Chlorine with lone pair electrons. Green was probably the worst color to pick, so let's try that again. Does chlorine have more electrons than hydrogen? Yeah, so we could potentially see it donate in. Our halogens are a little bit weird, so we'll come back to them in a second. We look at C. What do we see with C? Cool. Carboxylic acid. And when we look at the carboxylic acid, what do we see?
I like carbon.
Okay. Atom X is the atom immediately bound to the ring. Which is atom X?
Carbon.
The carbon. Okay, so very common. Oh, I see all those electrons. It must donate. Look at atom X. Does atom X have electrons to donate?
No.
No. In fact, if anything, what is that oxygen doing? Withdrawing electrons, making the carbon positive. That's a withdrawing group. That's not going to work. Which then sets us up with our last answer, ROCH3.
Which was the answer for the last one?
Yeah, that would be annoying, right? If they just had the exact same answer, so it must not be this one.
Yeah.
Okay.
Well, that's what I was saying.
Does the oxygen donate electrons in?
Yeah.
Yeah.
Yeah. Okay, so we've got two answer choices that could work. Either B for our chlorine or O for our oxygen.
Yeah.
What do you think?
Well, let's.
You told us that, we'll come back to the thing you said we're gonna come back to on halogens.
No.
Okay, then I guess we won't. We'll just stare at each other. No, here, let me see.
The last
Then should we
How many
write-
bonds can oxygen get up to?
Yeah, two additional.
3 with a positive charge, which means that oxygen can absolutely donate its electrons. How many times do we see chlorine with multiple bonds? Never.
But you just said
Which of these two answer choices makes the most sense as being the most activating?
D.
D, where it can donate those electrons in. So what's the answer? D.
What's the deal? Why'd you say the whole thing about you'll come back to it?
I said I would come back to it. So let's come back to it. What's the deal with our halogens? They do have electrons. So we could say, oh, because they have electrons, they could donate and they could be activators. Chlorine and our halogens, for that matter, do not like to share their electrons inwards. Okay? There's a variety of explanations you could go with. The easiest one is just to say they're electronegative. And I know there's a gaping giant freaking hole in that argument. Okay? I would argue the biggest explanation behind it is your chlorine is looking at group 3 or row period 3. You're looking at a 3p orbital. It can't donate those electrons in as effectively. So therefore, it's not able to share the electrons in. Okay? If it can't share the electrons in through resonance, then what's next? Induction. And now we look at the electronegativity. Chlorine being an electron withdrawing group due to its electronegativity deactivates the ring. Okay, so we get this weird gray area with our chlorine, okay, and with bromine and with iodine. Our halogens do sit on the exact line when we talk about the which has more or less electrons than hydrogen. Our halogens are the line. Okay? They are deactivators. They will slow an EAS reaction down. Okay? One of the other terms that should be floating through the back of your mind when we talk about the EAS reaction is not only activating and deactivating, but also a directing effect. Activators tend to direct substitution at the ortho and para positions. Okay? Deactivators tend to direct at the meta positions. So if atom X has more electrons than hydrogen, it is an activator and it is ortho-para directing. If it has less electrons than hydrogen, it is a deactivator and it directs to the meta position. Our halogens sit on that line. They don't like sharing their electrons. Therefore, they are deactivators. But because they have those electrons that sort of align with the ring system, they direct ortho-para. Okay? So the halogens float in a gray space where they take a little bit of both worlds. Okay? And I just remembered as I was saying ortho-para. When we go through to memorize those, if you do choose to memorize that, activators you should not memorize as ortho-para directors. You should memorize them as para-ortho directors. The para is a more likely substitution than the ortho for steric reasons. Deactivators are meta-directors. Okay? Activators, para-ortho. Okay? And if you got that memorized, that will hopefully... It's APO, right? A-P-O. No? APO? I mean, it works.
Like the motion
Kind of like
on the
your
left.
emotions about the class.
What's What's a boom?
I thought that was funny. See, what?
Oh, a boo, ha ha.
APO.
Oh, a boo.
Okay. So with that, we're done. We got some EAS out of it.